Good afternoon. How's everyone doing? It is afternoon, yeah, I've checked. Hi, I shall do my best to get between both sides of the pillar. My name is Ed Doxat, and I'm here with a slightly faulty clicker, it would appear. I'm here to talk to you about the latest automotive platform. There we go, it's going backwards. The latest automotive platform that Arm have released. So, as Suraj mentioned earlier this morning, in March this year, Arm released a series of new AE IP products, including the Neoverse V3AE core. We've also got the Cortex R82AE and a new interconnect and GIC, both suitable and qualified for AE use. So the work that the team have been doing now over approximately the last 9 to 12 months has all been targeted towards delivering a reference diagram, a reference design to show how all of these components can be integrated together and to provide a high-performance compute subsystem that has been extended with a safety island in order to host automotive safety-critical workloads. So this work is complete and is available publicly. We have an example software stack which is available to run on an Arm FEP. This is all available to download today. The other unique feature about this is that we've distributed all of the software stack in Yocto layers to make management of things a bit more straightforward. So what is this RD1AE? So we've taken an infrastructure class system design, and we've extended it by adding a safety island to provide an additional ASIL-D compute environment. So you can see the components that we've used in order to do that. So those are all integrated in one system to allow us to show this work. So the main features that we'll talk through today. So we've got a secure boot process, as was driven from the RSE element. We've got a safety island which is uses different numbers of Cortex R82AE cores, and we've got the new interconnect and the new safety-enabled GIC in that subsystem too. The safety island hosts a number of different workloads, including application monitoring. We've also got a high reliability compute subsystem for any general ASIL-D workload that you would look to host in an automotive environment, and a method of responding and handling system fault signals. We've also got hardware-backed cryptography support and the other features that you can see there, and we'll just step through those in the next few slides. So system boot, in order to provide a reliable and secure boot flow, which is important for any system, but all the more so for automotive, we drive the boot flow from the RSE, and that sets up and loads images from trusted sources for both the safety island and the primary compute. So this gives the system a known validated boot flow, so that you can be sure that your system is running the images that you expect, and those images are signed and can be securely provisioned to your system. We also boot either Linux or a Type 1 hypervisor. In our instance, it is Zen, and the safety island compute environment is available before the primary compute is, in order to allow you to perform any system health checks or hardware validation before the primary system becomes available. Just a quick note: if it's possible to get the slides on the TV in front of me, that would certainly help, please. So the safety island. This is the primary addition to the infra-based platform that we've started from. So you can see here we have 3 domains where the different workloads have been allocated. Domain 0 is responsible for the initial booting process, and also acts as a network relay. So there's a single network entry point into the safety island, and then network traffic can be distributed to other clusters as you require. The domain 1 in the middle, our allocation for this has been the safety oversight. So you can see the fault handling and the CAM service, both of which we'll step into a bit more detail in coming slides. They reside on domain 1, sorry, and domain 2. We've got an example ASIL-D type application. So we've ported some bits of AutoWare to run on that portion of the safety island. And you can also see that there's communications to and from the different bits of the system. So critical application monitoring. So this is the first use case that we'll talk a bit about today. CAMS, as we refer to it, is really here to help a system be able to detect when an application running on the primary compute exhibits some kind of fault, for example, a stuck-at hardware fault. And in this instance, what we have is a mechanism where the safety island is monitoring the applications that are running on other aspects of the system, and that we can analyze a message arrival and timing information and conclude if there's anything that's not happening in the order or within the time limits that we've specified on the safety island. The benefits of running it on the safety island is that you can make use of the lockstep and the higher safety rating of the Cortex R82. So that gives you a high reliability place to run the monitoring. Whereas if the monitoring was run on the primary compute, you wouldn't necessarily know if the monitoring platform itself had actually experienced the error. We synchronize the timers between the different aspects of the systems using GPTP. So this is a standard time synchronization protocol, which is part of the sort of suite of standards which make up TSN. This allows us to be confident around time stamping of the arrival of signals, so we can come to reliable decisions as to whether an application is performing as we'd expect. The inclusion of the application monitoring on the safety island allows you to have an overall higher ASIL level for your system, whereas without that you have to incorporate different error detection mechanisms on the primary compute. So here's an overview of the CAMS project. There's 2 phases of using CAMS and deploying it. So you have a calibration phase where you determine the behavior of your application. So you do that in a known good environment under ideal conditions. That gives you a database of messages that you can then use and check against when the application is deployed and executing at runtime. And if you see any violations of those timing or message orderings, then you can capture that instance on the safety island and then perform whatever recovery mechanism you think is appropriate. So this isn't an area where Arm has decided that a particular reaction to a particular fault is such and such. This is very, very context sensitive, and definitely something that people integrating systems with this kind of capability would look at doing a bespoke per deployment type of handling, up to and including just setting a flag and letting another piece of hardware in the system then respond accordingly. So another example that we've ported onto the safety island is to take a portion of the AutoWare software stack, abstract that to run on the Zephyr RTOS, which is the host operating system on the safety island. And the idea there is that we can demonstrate a really important part of the AutoWare software stack, so the bit that calculates vehicle trajectory. So we can demonstrate how you can run that sort of software in a higher safety environment than just running it on the Neoverse primary compute. So if you want to detect and trap or prove to have against runtime issues for determining acceleration, brake and steering inputs, then that's a really important function that you want to have running in a highest possible reliability platform that you can manage. These demonstrations are also available on an NXPS32Z device, so we've taken the same software and we've deployed it in a couple of different environments. The full RViz rendering requires hardware, the real silicon platform to run on because of the performance requirements. On the FVP, we've taken a subset of that example and demonstrated that on our system. Fault handling. So we had a question on fault handling the other day in this room about, I think, device tree. So this is a nice opportunity to present the work that we've done. So the system has got a number of fault management units across the different bits of the IP in the system. The signals that those faults generate are aggregated into the safety island, and we have a small Zephyr application which will track and respond to those error signals and then produce some kind of error signal out. This is not RAS. This is a different mechanism of gathering and processing error information. And as I think we said the other day, when you're designing and integrating a system that has got lots of different IP, perhaps from different suppliers and different third parties, the structure and topography of your fault management unit is going to be quite specific to the system. So it's a very interesting area in terms of standardization and other things that we can and can't do here. But so for the moment, what we wanted to do was to demonstrate one approach that you can take and show how that information can be consolidated into our safety island example. So some of the other features that I'll just go through quickly. So Type 1 hypervisor, in our case, this is Zen. Other Type 1 hypervisors are available. So we use this as an opportunity to demonstrate how VMs can be used to separate workloads and all the standard and good reasons why you want to put a Type 1 hypervisor in an automotive system. As you might expect, VMs need to communicate with other parts of the system. So we've got network abstraction with OpenAMP and VirtIO to be able to communicate to and from the safety island. The parsec services that are available, we've extended to have the crypto and storage capability provided by the RSE. So that's the cryptography, maths, and secure storage. That's managed now in a single reliable location. And the team are working right now on the integration with eWall and understanding how that can fit into the OneLab story that we've been hearing about this week. So that's a whistle-stop tour of the work that we've done. Wanted to leave time for questions at the end because it's quite a large subject matter to cover. So thank you very much indeed. And if you do have any questions, then please fire away. It is. Let me put this up to everyone, perhaps.
Hi, Ed.
Hi.
So just closing the loop on this RAS thing. Part of me thinks, oh, it's a shame it's not RAS, but then another part of me says, well, maybe RAS isn't fit for purpose in heterogeneous systems like this. So do you think you're on to the right way to do this sort of error handling?
That is an interesting question. I've got Felipe Rinaldi down here who can assist with the answer. But as you say, my understanding is some of the RAS mechanics don't naturally fit with some of the AE extensions. But Filippo, have you got?
Can you go back to the
Sure.
the one that shows the FMUs at least? It's pseudo RAS actually. To be honest, the device FMUs, they still comes from the same components that feed the RAS errors into the application cores. So it's not that you are missing RAS, you are kind of redirecting the RAS into the Cortex-R, because we still want the Cortex-R to be the first one to take, right? What we are still looking to, we need to kind of close the loop, is whether how, for example, the safety island can maybe interpret that. If it can do something about it, it might manage the error. But then ultimately, if it's not a fatal error, it can potentially still inject back that error into. So that's something we're still looking to see what's going to be the final shape, to be honest. Right.
Anyone else?
Gentleman in the front.
Hi, Ed.
Hello.
Elephant in the room question. How about safety certifications, and what's the strategy there from this tech point of view?
Yeah, as has been touched on a couple of times already this morning, automotive certification is certainly quite a piece of work. The example that we've got here and the software is provided in order to demonstrate the sort of things that you can achieve and the types of systems integration techniques that will help with safety. We don't intend this as a safety product. So the firmware is all derived from open source work and is provided as is. The intention being, if anyone wanted to take this or to build a system like this, then there's a separate safety analysis process that would need to be executed with all of the different standards to be applied for.
Yeah, follow up to that. So for the safety stuff, you need to have the paper trail to prove it.
That's right. Yeah.
So how much do you already have?
Okay. Well, I've got a fantastically simple answer to that. None. So our intention here, just to restate, this is an example system to inspire other people to take the next step. It's a process, as you know, with lots of before and afters, and requires a long ongoing ownership, and is very specific to an overall system. So doing the right work in the right context is really important. So that would be step 2 for someone.
And just clarify, your question is about the software, right? Because for the individual components, we still have the AE IPs, right? Which will have the paper track. Yeah.
Yeah.
Right. Okay. So there's partially some pieces of the hardware we do have, right? But not for the software or the integration of the safety island yet.
Question to her.
Yeah. Thanks for the presentation. I was wondering if the components, if there is the reference implementation for the components that are running on the safety island are open source and publicly available, or do you intend to build kind of a project around them that so we could be shared?
It's all open source, and you can download it over your lunch.
Thank you.
I have a question.
Sure.
When talking about S32G, you mentioned something called FVP. Could you just explain that to me?
Sure. So the S32Z platform is I think it's an R52 based chip from NXP. The software examples that we've shown here are available to run on our FVP, which is a fixed virtual platform, which is a models-based representation of the system, because it's providing a functional equivalent, but not a performant variant of all of the IP and the system's IP. You have a much lower level of performance, so that restricts the type of applications that you can run on that model. There are other people working on models to run at a faster rate.
Manish,
considering we are doing very time critical system, right? Does it make sense to invest in a real hardware, not doing it on models, software models?
Yeah. So the intention is that we can find a partner to work with to turn this into a reality. As you might imagine, there are other pieces of work that the team are doing on different platforms that aren't FVP to validate some of these timings and these interactions. At the moment, those aren't publicly available. What is available though is the software and the FVP. Yeah,
just like Ed said, most of these IP have been released now in March, right? So it's very early, and the FVP at least gives you a very, very early way to play with the new IP.
Okay. Well, another question? No? Well, thank you very much for listening. Enjoy your lunch.